Okay, so this is problem 4.75. I'm going to solve this using mesh analysis. Uh, so to find the Norton equivalent with respect to these two terminals, we have to find the V Thevenin. So the voltage across this 5.6K ohm resistor. And then we want to make another circuit and find the current I short circuit through A and B. So I'm going to go ahead and do this loop. I'm going to call it I delta, I1, and yeah, that should be it. So go ahead and write the equations. Negative 280 plus 2000 times ID plus 2000 times ID minus I1 equals 0. Second equation would be 2000 times I1 minus ID plus 2000 times I1 plus, sorry, this would be minus. Okay, so then 2000 I1 minus 0.2 ID plus 5600 equals 0. And then we can just plug this in. And we have I1 equals 1 over 50. And ID is equal to 2 over 25. So then to find the voltage across 5.6K ohm resistor, it would be I1 1 over 50 times 5600, which is 112 volts. Now we can redo this. Oh, here. And then we realized that the 5.6K ohm resistor cancels out because current travels through the path of least resistance. So the equivalent circuit would look like this. So we do mesh analysis again. ID. We have two equations again. So our I1 would be equal to our I short circuit. So then our equations would look like this. I have negative 280 plus 2000 times ID plus 2000 times ID minus I1 equals 0. And our second equation would be 2000 times I1 minus ID plus 2000 times I1 minus 0.2 ID equals to 0. So then we can plug this back in. 2000 times 3 0 thousand 50. So we get that our I1, which is our short circuit, is 3/50. ID is equal to 1/10. So I1 equals to I short circuit, and then this voltage would be our V Thevenin. So then to find our R Norton or R Thevenin, we have we know Ohm's law is V equals IR. So R is equal to V over I. So then 112 over 3/50 is equal to 188 or 1866.7 ohms. Then our Norton equivalent would be like this. We have a current source of 3/50, which is 0.06 amps. With a resistance of 866.7 ohms. So this is what our Norton equivalent would be with respect to these terminals.